Hello and welcome to Lab 3 on rectifiers. Today we're going to see why rectifiers are important. We're going to learn the steps to create a breadboard circuit from a schematic electronic diagram. We'll learn why we can't view the transformer output and rectifier waveform at the same time in a bridge rectifier circuit. And we'll show the function of filter capacitors in DC power supplies. Well, a guitar amplifier uses 300 volts DC on the plates of its anodes in the vacuum tubes. Well, how does it get that 300 volts DC from a 117 volt AC power supply coming into our house? It's through a rectifier circuit. In fact, almost all the electronic circuits that we use in our daily life use DC voltages that need to have some kind of rectifier circuit in order that we get power from the AC source. This is a power supply for a computer. This is the iPhone, what do you call that, the little wall wart that you plug into the wall to give it a DC voltage to charge it. And this is just some DC power supply for something. We're not going to go into the theory of how each type of rectifier works in this presentation in order to keep things short as possible. You've already covered this material in the lecture part of class. The first rectifier circuit we'll build will be a half-wave rectifier. Let's see how to construct this circuit on a breadboard. Well, we've got two leads coming out of our transformer and also the center tap. We're going to put that center tap right there because we're not going to use it. We're just going to keep it out of the way over there. If we just let it hang, it might touch something and mess things up for us. Notice that I put one of the leads onto the ground and one of the leads is just sitting over here waiting to be connected up. Okay, yeah, so here's the center tap that we have going nowhere. There's the lead from the top part of the transformer sitting down there. There's a lead from the bottom transformer going into the ground. Notice that we have the ground bus, which is all across here, connected to this terminal, which is our black terminal, and then we're going to use that for an external connection that'll connect the grounds of our oscilloscope. Notice that we've got the ground on the top here, and we've got this part of the transformer down here. Don't let that mess you up. It's just we had to invert that because of the way the proto board was set up here. Okay, well here we go. So here's this wire coming out of the transformer, and I know I have to connect it to a diode. There's the diode going in the direction that it needs to go with the little line there to show you the head end of the diode. And then on the other end of the diode, we need to connect a 10K resistor. That's right there. There's that 10K resistor. I just put it right over there to ground, just like this 10K resistor is connected on one side to the diode, which is right there, and on the other side to ground. And that's the circuit. The circuit's done, but we need to tap the circuit so that we can make observations in the circuit. So now I've got a green wire and a yellow wire on these lugs here so that I can connect external observation devices. We always use color codes. We're not going to use red here or black here or blue because we reserve those colors for our power supply. Okay, let's connect the green wire to this point between the diode and the resistor, which is right there. So I just connected the green wire there. We connect the yellow wire to this point between the diode and the transformer. There's the diode, and there's where the transformer is. So that's that point in the circuit. And we're ready to go. We just have to hook up our oscilloscope. There's channel 2 connected to channel B here. So I took channel 2. The ground is connected to our common ground that's connected across that bus, and then there's the hot wire for our channel 2, and then here's our channel 1, which is connected to channel A here in our circuit diagram, and it's connected to the yellow wire through that external connector. And we're ready to start our observations for our first circuit. Well, for the next part of the lab, we'll need to make use of the center tap of the transformer. So we're going to take that wire that we had, it was sticking over here to keep it out of the way. Now I moved it forward, so it's going to be part of our circuit. And notice that I connected it to ground with a little black jumper wire. Again, we're using that color code. We're using black wires whenever we're connecting to ground. to keep things straight in our circuit. Now, from that wire, we have to go through a 10K resistor to some point over here. There's that 10K resistor going from that point in the circuit to some point where I'm going to connect to the head end of a diode. There's the head end of that diode. The other end of the diode is, of course, connected to the transformer wire. Notice we have the top end of the this top end of the transformer here is now going up here. So now we've got our pictures the same orientation, which is always nice. Okay, but it's not essential. I made a little wire right here. Just, you don't need to have that jumper there, but I moved it over here so that I can make that diode in the same direction as this diode, just to help keep everything straight and easily visualized in my breadboard circuit. Well, there's my diode with the head end right here, and then the tail end is going to the other end of my transformer. Now the circuit is complete. This circuit is complete, but I haven't tapped either of these 2 points in the circuit using my external connectors there. So let's put the green wire right here between the resistor and the diode and the other diode. There, all those 3 things are connected right there. So I put my green wire there. Put my yellow wire, I'm tapping that point for channel A, which is the point coming out of the transformer and going into that diode. There's the circuit. Isn't it beautiful? And that scope is ready to be connected. So I connect channel 2 to this point in the circuit, which is our green wire. Connect channel A to this point in the wire, which in the circuit, which is our yellow wire, and we're ready to go. Okay, for the last circuit of our lab, you are going to connect that one. So it's up to you to breadboard that one, just like we've breadboarded the other 2. Okay, here's an important note about the bridge rectifier. Let's say that, let's first take away the, see here we have a ground in our circuit that we were given, but I'm going to take that ground out so that we can look at the output of the transformer and then see what the voltages are in our circuit without this ground, and then we'll put the ground back in a minute. So let's say we just, for the sake of argument, we have a plus minus 10 volt AC wave coming out of the transformer. So when the transformer is giving us a 10 volt on this wire, that's this part of the waveform, and we've connected the ground of our oscilloscope to this point of the transformer, which we're calling now our 0 volt reference. That's our ground in the circuit. We don't have a ground here anymore. And then when the waveform goes down to here, it's at the negative 10 volt peak, and that point is still at 0 volts because I've got my ground reference on that. So that's how our voltage is going to look like in our oscilloscope if we hooked it up like that and there was no ground in our rectifier circuit. Well, let's trace the current path when the transformer has this polarity. There it goes right along here, and it has to make a choice. Which way is it going to go? Is it going to go left or right? Can't go through that guy because he's reversed biased, as you know from class. So he's going to go through this diode, which is forward biased, and whenever we have current going through a forward biased diode, we have that 0.7 of a volt drop. So we started out at 10 volts and now we're at 9.3 volts. There's the current going. Now it had a choice at this point. Could it go this way or this way? It's not going to go through that guy because he's reverse biased. So he's going to go through the load resistor. What voltage does he come down to? We don't know yet, but we'll know in just a moment. As we see the voltage drop across this diode has to be 0.7 volts. And since we had referenced this point of the transformer to 0 volts, we know that there was a 0.7 of a volt drop across this resistor. So if this is 0 all along here, that must mean that this point right here is at plus 0.7. See that? So now that we know that this is at plus 0.7, and we already knew that was at 9.3, that gives us an 8.6 volt drop across our load resistor. Notice that this point where we had referenced at 0 that I took out earlier is now at plus 0.7 volts. It's not at 0 because we have put that point in our circuit at 0. And if we went through the opposite way, where this is still 0 and now this is at the negative 10 volts, the current is coming like this through the rectifier circuit, and I'm not going to march through that, but you can look at it. The one thing I'll point out is that when we had the, at this point of the waveform, when this is at negative 10, now this point in the circuit is down to negative 9.3 volts. And that was at 0, so this is important. Also notice that we still have an 8.6 volt drop across the resistor. It's just going from negative 0.7 to negative 9.3 instead of how it was when we had this part of the waveform. Now, here it is. You might think that you could hook your oscilloscope up like this to watch the output of your transformer on one channel and then the output of the load resistor on the other channel, and then you would see both of these waveforms at the same time. But don't do that. The reason why is because the grounds in our oscilloscope are not floating. They're not independent. They are connected internally inside the oscilloscope. So what that means in our circuit is that if we connected this and this to grounds, these 2 points are connected through the oscilloscope, and when we start our transformer, the current path is not going to go through here. It's going to bypass that route that we want it to go, and instead it's going to go through your oscilloscope right to this point, and the current will go right across your diode here, and you'll get a 10 volt drop across your diode. And we never want that, because you always want to have a current limiting resistor whenever you have a diode. You got to put that resistor in series with it, otherwise you can have too much current in the diode and it'll blow it out, just like that one was. Okay, so here's how we have our circuit hooked up with a ground here, no ground here, and we're not looking at the output of the transformer. Instead, we've got our oscilloscope with a common ground right there. Both channels are going to the same ground, and we're looking at channel A and B. Let's see what we would observe. So when the polarity of the transformer is thusly, we've got 9.3 volts coming out here. We see 8.6, and this is 0. So now I'm referencing, I changed all the voltages in the circuit because now instead of having my 0 point there, I'm making my 0 point there by putting the ground reference in the circuit at that point. So we're seeing this 8.6 volt drop across the resistor. And now when the current goes the other way, see, no, we're still going the same way. What did I want? Oh, so I wanted to point out that in channel A, what channel A sees here is its lead is going at this point in the circuit, and here's its ground. So it's just looking at the voltage across that diode when the signal, I should say the output of the transformer has that is going that way. So then instead of seeing the whole signal like we'd like to see out of the transformer, you're going to see that just bias voltage of that diode. Okay, here's the other way. So here we had plus down here and negative 0.7 here. Now it's going to go the other way for the transformer. We've still referenced that point at 0, and this point again is at 8.6 volts. I'll let you walk through that if you'd like. Well, most rectifier circuits have filter capacitors to smooth the bumpy output through the load resistor. But we did not have a filter capacitor on our load resistor, and we got this very bumpy output of our rectifier. Well, that wouldn't be good for a power supply. In a power supply, you put in these capacitors. Here's a small capacitor, and you can see, well, it's making it a little bit more like DC, but not much. I increased it to 10 microfarads, and now we've got sort of a reasonable signal. Just we call that ripple on there. And now I've increased it to 1,000 microfarads, and you can see it takes a little while for the voltage to build up because this capacitor has to charge up, but once it charges up, you've got a very nice DC voltage that's coming out. It doesn't look like this anymore. So the idea of a power supply is you don't want the output to be choppy like that. You want it to be like this. Well, we hope you've enjoyed the show. Thanks for coming along today.